You just looked at your phone, just like that, for no reason. No one called you, nothing beeped, you just picked it up and looked at it. Maybe it was 30 seconds ago. Maybe right before you started watching this video. And here's what will surprise you. This very movement, unconscious, automatic, almost reflexive, is a direct consequence of what happened to your ancestors about 1.8 million years ago. Over nearly 7 million years of evolution, the human brain has tripled in size. Tripled, this is not a metaphor. The earliest Homo erectus skulls, dating back 1.8 million years, contained a brain with a volume of just over 600 milliliters. By 500,000 years ago, that volume had exceeded 1,000 milliliters. And now, inside your head, there's about 1,200 milliliters or more. But here's the mystery. The brain is the most expensive organ in the body. It devours resources. It makes childbirth deadly. It prolongs childhood to such an extent that human infants remain helpless longer than the young of any other creature on Earth. By all the laws of evolution, a large brain should have killed us. But it didn't. Why it grew so large is one of the strangest stories ever told. The brain accounts for about 2.5% of body mass, but consumes about 20% of all the energy the body expends at rest. By way of comparison, a leg muscle at rest uses almost no energy. The brain is always working. It never shuts down. For a person who is simply sitting and doing nothing, 1 out of every 5 meals goes exclusively toward nourishing the brain. Now imagine this in the context of the savannah, where food is scarce, where you have to hunt for it, where sometimes you go without eating for several days in a row. Throughout the first 2/3 of our evolution, our ancestors' brains were in the same size range as those of other modern apes. Yet we share about 99% of our genome with chimpanzees, a 1% difference, and such a chasm. Scientists are still debating what exactly set this process in motion. But 3 theories have stood the test of time, and each of them will change the way you look at something very familiar. Chapter 1. Fire and the Gut. How can a species even afford to have a large brain if its body can barely maintain a caloric balance? The answer didn't come from a neuroscientist. It came from a primatologist who had spent many years studying chimpanzees in Uganda and had once tasted their food. Richard Wrangham, who spent 20 years studying wild chimpanzees in western Uganda, concluded that no human could survive for long on such a diet. Our weak jaws, small teeth, and short intestines are simply unable to extract enough calories from raw fruit to sustain a large body. Our weak jaws, small teeth, and short intestines are simply unable to extract enough calories from raw fruit to sustain a large body. In 2009, he published the book Catching Fire, How Cooking Made Us Human. The essence of his argument is simple, almost brutal in its logic. When food became easier to digest, the body expended less energy on digestion and obtained more calories from every bite. And the brain is expensive. The brain devours energy. On a low-calorie diet, when the whole day is spent chewing, it's impossible to sustain a large brain. Fire solved this problem. But how is this biologically related to brain size? This is where the hypothesis comes in. Without it, the story doesn't hold together. The communication between the gut and the brain is a key idea in the expensive tissue hypothesis, proposed by Leslie Aiello and Peter Wheeler in 1995. Primates with smaller guts relative to their body mass were found to have larger brains. Aiello and Wheeler calculated the number of calories that the species saves thanks to its smaller intestine and showed that this savings exactly matches the additional cost of a larger brain. Primates that expend less energy on their intestines can afford to have more brain tissue. In other words, your brain grew because your ancestor learned to chew less. What you call making dinner is actually the oldest form of biohacking in the history of life on Earth. Chapter 2. The Social Game. But energy is only half the story. Because here's the question. Why do you even need a big brain if you already know how to obtain calories? In 1992, British evolutionary psychologist Robin Dunbar published a paper in the Journal of Human Evolution that revolutionized our understanding of why the brain grows. He measured the size of the neocortex in different primate species and compared it to the size of their social groups. 47. Through rigorous statistical analysis, Dunbar demonstrated a clear correlation. The larger a primate's social group, the larger its neocortex. Through rigorous statistical analysis, Dunbar demonstrated a clear correlation. The larger a primate's social group, the larger its neocortex. Dunbar's social brain hypothesis states that brain size is directly related to group size in mammals. The larger the group, the larger the brain. Why? Because living in a group is not just a matter of standing next to one another. Primates, including humans, live in complex social groups where survival depends on cooperation, deception, forming alliances, and resolving conflicts. Unlike solitary animals, primates must recognize specific individuals, remember past interactions, predict the behavior of others, and maintain social bonds, all of which require cognitive resources. Dunbar proposed that the number of people with whom a person is capable of maintaining genuine relationships is limited by the very architecture of the brain. Based on the size of the neocortex, he calculated that the optimal human group size is about 150 people. This number has gone down in history as Dunbar's number. This pattern is confirmed among traditional hunter-gatherers. Even among people living in industrial societies, the number 150 retains its significance. The Hadza people of Tanzania, one of the last surviving hunter-gatherer groups on Earth, still build their camps around precisely such a core. The Hadza, like other hunter-gatherers, have flexible social structures and a high rate of migration between groups, but their core population size remains close to the Dunbar limit. The brain grew because the social game was becoming more complex, and it became more complex because the stakes were rising. Those who can read others' intentions survive. Those who cannot do not. What you call reading between the lines in someone else's message is actually 1.8 million years of neural training. Chapter 3. Instability as a driving force. But this part of the story will surprise you the most. Many people think that the brain grew because our ancestors became smarter and that made them more successful. It's logical. It's obvious. And it may be wrong. In 2024, Mauricio Gonzalez Ferrero, a researcher at the University of St. Andrews, published a mathematical model of hominin brain evolution in the journal Nature Human Behaviour. The human brain tripled in size over 4 million years, but why this happened remains an open question. His conclusion is unexpected. The absence of direct selection for brain size or skill level in his model contradicts the long-held view that brain enlargement was driven by direct selection for enhanced cognitive abilities or behavioral complexity. In other words, perhaps the brain did not grow because the smart ones survived. The brain enlargement modeled by this theory is not caused by direct selection for brain size, but rather by its genetic correlation with development in complex ecological conditions and accumulated culture. The environment was unstable. The climate was changing. A comparison of glacial and interglacial periods shows that the physiological costs of a large brain became particularly disadvantageous during periods of warming. This created pressure from both sides. A brain that was too small meant you wouldn't survive. One that was too large was too costly for the body. This evolutionary shift coincides with the emergence of cognitive and cultural innovations, symbolic tools, and language which may have made it possible to offload part of the cognitive burden externally. The Aka people of the Central African Republic are one of the few hunter-gatherer groups that have preserved the tradition of collective knowledge transfer between generations. The elders pass on to the young not just skills, they pass on accumulated maps of reality. This is precisely the accumulation of culture without which the brain cannot grow. Analysis of fossilized skulls shows a trend toward accelerated brain growth in later lineages. The closer it came to us, the faster it grew. Not because we adapted better to nature, but because we created an environment and began to adapt to that environment itself. But here's what no one mentions in this story about the triumph of evolution. The cerebrum nearly killed us. Literally. An increase in brain size hypothetically offers cognitive advantages, but comes with costs associated with the growth and maintenance of energy-intensive neural tissue. A human newborn comes into the world with a brain that is only 25% developed. In chimpanzees, it is 45%. This is because if the brain were to continue maturing inside the womb until it reached the necessary size, no woman would be able to give birth. The pelvis simply couldn't handle it. This is called the obstetric dilemma, and the solution is to give birth early, as premature infants, and let them continue developing outside the womb. This means that the human child is the only primate that requires the care of several adults at the same time. A mother physically cannot manage on her own. It is precisely this, it seems, that spurred the development of language, storytelling, and complex social bonds. The large brain necessitated the building of villages, and the village, in turn, made the brain even larger. Dr. Thomas Puschel, lead author of the 2024 study, says, major evolutionary changes do not always require dramatic events. They can occur through small, gradual improvements over time just as we learn and adapt today. This is important because we're used to thinking of evolution as something that's already over, with a final version, that the brain you have right now is the result, not the process. But think about it. Everything you consider a weakness depends on other people's opinions. The inability to eat alone in public, the anxiety you feel when you're excluded from a group, the compulsive urge to tell someone something funny right now, immediately. These aren't weaknesses. The key to understanding the evolution of our species lies not so much in the fact that a large brain enabled the formation of large groups, but rather in the emergence of a new pattern of attachment, one that depends on cognitive resources, but is emotional in nature. You cannot live without other people because 1.8 million years ago, being without a social group meant death. You reach for your phone because part of you is still checking. Am I still in the group? Have I been left out? You're here. You're watching this. You're thinking about it. The increase in brain size is one of the most obvious evolutionary changes in human history, inextricably linked to our unique cognitive and behavioral traits. The very fact that you're asking this question is the answer. Your brain was made for this moment. If you liked it, subscribe. Follow the channel so you don't miss out on lots of informative content.